Hey, we're back at it again with some notes today. Let's talk about inverses, inverse relations, inverse functions. Let's get to it. Okay, an inverse relation maps output values back to their original input values. It's basically taking us completely backwards through a function or relation. Instead of plugging something in and getting something out, what if we wanted to do that process backwards? Take those outputs, plug them into something, and get back the original input. That's what an inverse relation does for us. Okay, so that's what we're talking about today. In other words, our x and y's, our inputs and outputs, end up being swapped in an inverse relation. The notation we use for the inverse of a function, so let's say it's called f of x, is written as f inverse of x. So this little -1 that's written up here as a superscript, kind of like an exponent would be, is just notation. So this is f inverse of x. Okay, so there's our notation. If a relation and its inverse are both functions, if they would both pass our vertical line test, or every x has exactly one y, they are called inverse functions. Okay, but that's only if both a relation and its inverse qualify as functions. We call them inverse functions. You don't have to worry about this too much. Okay? So let's do an example. Here is a function g of x defined below in a table. And it says what are the points, or asks us what are the points on g inverse of x. Okay, so we notice we have some points on here. 1, 7, 2, 10, 3, 13, 4, 16. 4 different points in this function g of x. Okay, so what are the points on our inverse going to be? Well, remember, in our inverse function, we're going to have a table where I want to plug in these values. Apologize for my lines here. We want to plug in these values that we originally got out. So I want to plug in 7, and I want to get back 1 for y. I want to be able to plug in 10 and get back the value of 2. And of course, I want to be able to plug in 13 and get back a value of 3. And I want to get back, plug in 16 and get back a value of 4. Okay, so the inverse g of x should look like this. And again, you might notice from our definition that really the only two difference between these tables is that the x and y values are swapped. Okay, so how would I find a function that would take me backwards? How would I get a function that would give me back those values? And it's actually a lot easier than it sounds. Okay, to find an inverse equation, first thing we're going to do is replace any function notation with y. So if it says f of x or g of x, whatever it is, we're just going to replace it with y if necessary. It might already say y equals. Okay, then to find our inverse, we're going to swap x and y. We're going to change our input and output variables. Don't change any values associated with them, just literally write y where x was and x where y was. Okay, then we need to kind of quote unquote solve for y here. We need to get y by itself and positive on one side of the equation. It doesn't matter which. Okay, so let's try an example. For g of x equals 3x plus 4, find g inverse of x, or the inverse of g of x. Okay, so running through our steps, step 1 is to replace f of x with y, in this case g of x. So we're going to come to this top function, and where g of x is, we're going to write y. And then we're going to write the rest of our equation equals 3x plus 4. Okay. Step 2, really important when we're finding inverses, swap x and y. So instead of y equals 3x, we're going to have x equals 3y plus 4. So y became x became y. That's step 2. Don't change any of the numbers. Don't bring the 3 over here with the x. Okay, it stays put. And lastly, we need to get y by itself. Okay, so to do this, to get y by itself, we need to get rid of these two values held onto y here. Let's first subtract 4 over. X minus 4 equals 3y. And then divide everything on both sides by 3. So we either have y equals x minus 4 all over 3, which would be acceptable as an answer, or you could also separate them as the value in front here, 1x divided by 3 is the same as 1/3 x minus 4 over 3. And the only reason you might write it in this form is it looks more like an equation of a line. However, if you're plugging in values, the version we had over here, which was x minus 4 all over 3 equals y, these are both acceptable values. They're both correct inverses here. This just looks more like y equals mx plus b form. So good to know that we can have either one. Okay, let's try our next example. For f of x equals 5x minus 10, find f inverse of x. So once again, step 1, replace f of x with y. Step 2, swap x and y. Step 3 is we need to get this y by itself. So we're first going to add this 10 over to the other side. X plus 10 equals 5y. Of course, those cancel. And divide everything on both sides by 5. Okay, so I could write this as x plus 10 all over 5 equals y. Or, again, you can think of there being a 1 here. So this is really the same as 1/5 x plus, well, 10 over 5 reduces to 2. And so here is 2 acceptable answers for our second question. X plus 10 all over 5 equaling y, or 1/5 x plus 2 equals y. Okay, so a question might be, how do I actually know if these are the correct inverses? Well, one thing you can do is, let's say I want to plug in a value. I'm just going to pick an x value randomly here. Let's plug in 1 to make it easy. So I was going to plug that in. 3 times 1 is 3, plus 4 is 7. So in this original function, when I plug in 1, we get back 7. Okay, so what should be a point on my inverse then? Remember that the x and y coordinates swap. So let's check if we have the correct inverse. And I think the second version down here is going to be easier to plug into. So remember, in the inverse, if I plug in 7, we should be getting back 1. So let's plug in. 7 minus 4 is 3. 3 divided by 3 is 1. Hey, look at that. Looks like we have the correct inverse. You could arbitrarily pick a nice easy point here as well. Let's say this time we plug in 2. 5 times 2 is 10. Minus 10 is 0. So plugging in 2 gives us back 0. Sorry for a crummy 0 there. So on our inverse, if I plug in 0, I should get back 2. So let's check. If I plug in 0, in fact, it doesn't matter which one this time. Let's try this one. 0 plus 10 is 10. 10 divided by 5 is 2. 0, 2. So we definitely have the correct inverses here. Okay, let's do our last example here. This time it's giving me a slightly more difficult one to work with. We have a quadratic. But again, let's go through our steps. So we're replacing h of x with y. Swapping x and y. And then getting this y by itself and positive isolate y. So we're going to start by adding 2 over. X plus 2, that's a 2, equals y squared. And now remember, to undo an exponent when something is squared, we use the square root. That's the opposite operation here. But remember, when we have something that's squared, we also get 2 possible cases. So we really end up with plus or minus the square root of x plus 2 being equal to y. And so in fact, you'd actually have to graph this as 2 separate equations to get the full inverse relation. And because if I plug in a value for x, we're going to get a plus case and a minus case, this is actually not a function. The inverse of this graph would not be a function. In fact, the original will be. We'll look at this graph in a little bit, but its inverse is not. Okay, so in fact, let's take a look at the graphs of the previous 3 examples and the inverses we found. So we're going to check out and see if we can see something that happens graphically. Okay, so here's a lot of information. We've got a lot of graphs going on here. But know that each one of these examples we just did, g of x, f of x, and h of x, these are the same three graphs that were on the last slide. And the original functions are all in blue, and their inverses are in red, or in this case, when I had to graph two different parts, red and green, the positive and negative case there. Okay, so do you see anything that relates each of these original graphs in blue to the graphs in red? Okay, or red and green, the inverses here. Okay, and at first, it's not super likely that you see it. Okay, but what I'm going to do is we're going to graph the line y equals x. Okay, and so that's done here in yellow. Y equals x. That's the line graphed right here. That's a line with a slope of up 1, right 1, and a y-intercept of 0. I've also added some points that are on the original graph and its inverse point for emphasis. And maybe now the relationship between these two is a little more obvious. Okay, in fact, I'm going to add in the other graphs here, also with some points in our line y equals x. And see now if you see a relationship between all of them. If it's not apparent yet, the answer is that each of these graphs is reflected over this line. This is a line of reflection for graphs and their inverses, y equals x. Which kind of makes sense, I guess, because we're switching x and y, so the line where x and y are exactly equal ends up being kind of a mirror or focal point for a mirror. Okay, so all inverses are reflected over this line y equals x. Make sure you have that in your notes, that's important. We'll definitely see some questions that go along with that. Okay, what if we wanted to know if a given graph's inverse will be a function? Right? We said in that first slide that the two answers we got, that plus and minus square root answer, would end up not being a function. How could I figure that out if I was just given a graph and I was asked, will its inverse be a function? Okay, is there a way to do that without having to graph it and find its equation? What we're going to do is take a look at our original graph here, h of x, and here's our inverse, this time graphed all as one color, a nice red here. So if I wanted to know if this inverse was a function or not, we learned last time about the vertical line test. So we could draw a nice vertical line and tell, will that pass through my graph more than once? And of course, yes, here it will pass through my graph more than once. Right there and right there. We see it fails the vertical line test and is not a function. Okay, that's easy if we have the inverse graph waiting for us. But what if I only had the blue graph? And I wanted to know, without finding the equation, without graphing it, would its inverse be a function? Imagine kind of flipping this red graph back up so it was standing upright here. What would this vertical green line appear like on our original graph? And the answer is it would appear like a horizontal line. Okay, not exactly in the same spot, but hopefully we get the idea here. That a horizontal line on the original graph plays the role of a vertical line on the inverse. Okay, so if we want to know if a given graph's inverse will be a function without finding its equation and graphing it separately, we have something called the horizontal line test. Okay, the horizontal line test tests if a graph's inverse is a function or not. And it's the same idea as that vertical line test. If a line passes through more than once, not a function. Okay, so we don't have to write out all the extra words. Hopefully we understand it's kind of the same premise as the vertical line test, just testing if an inverse of a current graph is a function or not. Okay, so let's do an example. Use the horizontal line test to determine if each graph's inverse is a function. So here's our given graph. Will its inverse be a function? So let's say again, if I want to draw a horizontal line, any possibly drawn horizontal line. So if I pick here, hopefully we can see right away, absolutely not. this thing is crossing my graph, in fact, 3 different times here. And we know to be a function, it can pass through at most 1 time. Its inverse is not a function. Okay, this fails the horizontal line test. Okay, one last example, almost done. Okay, what about this one? Hopefully here we can see if I pick a horizontal line, and we can do that anywhere, no matter where I'm able to drag that line to, at most it's going to go through my graph here 1 time. So even though this original graph is not a function, the horizontal line test tells us that its inverse is a function. This passes the horizontal line test, and its inverse is a function. Okay, that's it for notes today. Thanks for listening.